Hey everyone, gonna go through the practice exam here. Put it in a Word document like this to make it a little easier to follow. So we're going to start with question one. Now for some of these, I have them marked with this randomized right here. The order of these answers will be different for you, but that shouldn't be too much of a problem. So for question one, we're going to consider a regression output table, which I'll bring up right here. Which of the following is the correct interpretation of the adjusted R-squared value? So I go in here and I describe the regression predicts the price of a car in dollars based on fuel efficiency, engine power, acceleration, and the weight of the vehicle. And I'm asking about the adjusted R-squared. So the adjusted R-squared is found right here. It's 0.1303, which in percent terms would be 13.03%. So 13.03% of the variation in price, which is what we're trying to predict, can be explained by variation in the x variables, which are these. But the adjusted R-squared has a penalty for every variable you add to it. So penalized for losses in degrees of freedom, because every variable you add loses a degree of freedom. This is 13.03% of the variation in prices can be explained by variations in the x variables. Again, penalized for the losses in those degree of freedom. The regular R-squared doesn't have that penalty, so it's important to understand the slight distinction there. The adjusted R-squared, it's still the percent of variation in price explained by the variation in your x variables, but there is that penalty associated with it because every variable you add takes away a degree of freedom, and if your variable isn't contributing a lot of predictive power, the adjusted R-squared will go down because the loss in degrees of freedom is not matched by how well the variable is helping you predict. So then we go down to number 2. Again, same regression output table. So which variables are statistically insignificant? We go back here. What you want to look at is the p-values here. You can also use this using the t-statistics or the confidence intervals, using the rules that we've talked about before. Does the confidence interval contain 0? That'll tell you for the 95% confidence level if it is significant or not. T-score, you could look up that against a critical value in the t-table, but easiest way to look is to look at these p-values. And if these p-values are larger than 0.1, then this coefficient is statistically insignificant. The smaller the p-value is, it might be significant at the 10% level if it is 0.1 or less. It might be the 5% level if it's 0.05 or less. It could also be statistically significant at the 1% level if it is less than 0.01. And that's the case for miles per gallon and for weight. When the p-value is 0, that means it's significant at the 1% level because that's the lowest level of significance we track. So that's as significant as any variable could possibly be. So when we're trying to figure out which ones are not statistically significant, it's horsepower and acceleration, because these two p-values are much larger than 0.1. So it is statistically indistinguishable from 0 at any significance level that we care about. Then for number 3, what would you predict the price difference between two cars if one gets 10 miles per gallon more, assuming the cars are otherwise identical? So what that means is, if you plugged in the same number for horsepower, acceleration, and weight, what would the difference be if one car had a 10 mile per gallon advantage over another? And the way you would quantify that is, you take this coefficient, this is what the price is expected to change for every mile per gallon that car gets, how fuel efficiency increases by 1 mile per gallon. So to find out what happens if it is 10 miles per gallon better, you just multiply this coefficient by 10. And so you end up with 1,520, and then 1,521. And then I had a little bit of a range here, but it is 1,521 and 92 cents, basically. You just multiply this coefficient by 10, and that's your answer. And on the exam, I try to give ranges to make it a little bit less exact, so that you don't run into problems of missing points because of small rounding errors. In this one, though, not really necessary. You're just multiplying a number by 10, so you're just moving the decimal place over 1, but still. Then, considering this regression output table, an F-test is performed on horsepower and acceleration. Now, why might you choose to do this? If you see a group of variables in a regression that are insignificant, you might think that you're going to drop them from your regression because they aren't providing anything. But before you drop them, it's a good idea to do a test, this being an F-test of the variables that you think you're going to drop, and see if they are jointly significant. That is, can you say that both of these coefficients are 0 at the same time? And if you can say that, then you can drop them safely. So the null hypothesis in the F-test is that all the coefficients being tested are equal to 0. The alternative is at least one of the coefficients is not equal to 0. So here's our test. We're saying that this coefficient for horsepower and this coefficient for acceleration are both equal to 0. Then we look at the p-value for this test, and this p-value has the exact same interpretation as the p-value for a t-test. That's the advantage of the p-value. It is equal in all of the forms of testing. The rejection rule is the exact same. So we're looking for, is it less than 0.1? Is it less than 0.05? Is it less than 0.01? This p-value is 0.59, so it is much larger than 0.1. So this is statistically insignificant, which is an equivalent way of saying we cannot reject this null hypothesis that both of these are equal to 0. And so because we fail to reject the null, this null, the answer is both horsepower and acceleration coefficients are statistically 0. Then we do the same thing, and I just do this to clarify what the interpretation of the S-test is. We perform an F-test on miles per gallon and weight, which again, that's what this F-test is. Again, the null hypothesis is this coefficient is equal to 0, and this coefficient is equal to 0. Now, we have no reason to suspect that either of those things are true, because both of these are highly statistically significant on their own. But the point of this question is, we look at the p-value, it's basically 0, it's highly significant, certainly significant at the 1% level, it is smaller than 0.01, and therefore we can reject this null, but rejecting this null tells you something very specific. When you reject the null of the F-test, the result is at least one of the coefficients that you're being tested are statistically different from 0. The F-test only tells you that either all of them are statistically insignificant, or at least one of them is statistically significant. The F-test does not tell you how many of them would be statistically significant, if there is more than one, or which one is statistically significant. So, just based on an F-test, all you can say is that one of miles per gallon or weight is statistically significant. You would need to look at other information in order to figure out which one is statistically significant, if there's a difference. In this case, they're both highly statistically significant individually, so there's no real mystery here. They're both different from 0, but the F-test alone can't tell you that. You need to go looking at these individual tests to figure out if either one of them is, or maybe try to identify if there's a large group of these variables, which one is statistically significant. It's a little bit trickier to do when cases aren't so clear-cut like this. But the f-test only tells you one of them is different from 0. It doesn't tell you, or at least one. It doesn't tell you which one, and it doesn't tell you how many. So then for number 6, we're going to optimize this equation right here. I include this round to the second decimal place. This is just sort of a boilerplate thing I put on any numeric answers so that we don't include negative signs, because I figured out negative signs in your answers will break the Sakai answering for whatever reason. Still haven't figured out why, but don't put negative signs into your answers, even if they're required. And round to the second decimal place, although again, this won't be required sometimes as well. And this is one of those cases. So here's our equation. Y equals b raised to the third power minus 147b plus 537. So if we're going to optimize this equation with respect to b, we're going to need a first order condition, which is to take the derivative of this equation with respect to b, because that's what we're optimizing with respect to, and set that derivative equal to 0. So the derivative would be 3b squared, bring the b down, subtract 1 from the exponent, minus 147. The derivative of b with respect to b is 1, so you're just left with 147 here. And then this constant falls out because it doesn't change with respect to b, so this just becomes 0. So this is our first order condition. 3b squared minus 147 equals 0. 3b squared equals 147. Just move that to the other side. Divide each side by 3. We'll get 49. And then the square root of 49, take the square root of both sides. The answer is 7. Square root of 49. Now, you don't have to put 2 zeros after that if you have an exact answer like this. This is just, again, if you have it to these decimal places, that's the level I want you to round it to. Now, for this one, there's a picture associated with it. Now I'll get that here. So confidence interval of proportions. When you're doing the confidence intervals in a proportion, you're going to want to use the sample proportion, p hat, as the basis of your standard error. The easy way to tell this, the easy way that I use, is that when you're doing a confidence interval, you don't have a preconceived notion of what the answer is when you're calculating the confidence interval. You're only using the sample p, and you're building a confidence interval around that. For a hypothesis test, you have some preconceived notion of what the proportion should be that you're testing against, p naught. So if you have one of those, and it's actually involved in the test that you're doing, then the standard error will include that one. But if you just want to memorize it, p hats go in confidence intervals, p naughts go in hypothesis tests. That's probably just the simplest way to go about it. So the answer here is C. Back to our regression output table. There's a little bit of confusion on this one, so I'll just go ahead and tell you. This constant is itself a coefficient that you're estimating. If you remember back to the videos where I derived b1 and b naught, I had to derive both of those. This constant is the y-intercept b naught, and it's a coefficient that you're estimating as well. So if the coefficient is not statistically different from 0, and in this case, it's not, this is larger than 0.1, Not by a whole lot, but this is, in the strict sense, insignificant. So you cannot reject the null that this is 0. At the 10% level, which is the level that we generally care about as our cutoff point. So this coefficient is 0. So this constant doesn't go into this calculation because we're only looking at things that are statistically different from 0 at the 10% level or higher, obviously. So the constant doesn't factor in, the acceleration doesn't factor in, and horsepower doesn't factor in. So you're left with just miles per gallon and weight. And if I go back up here, see if I can get both of these on at the same time. This is how you get stata if you're trying to use it. If you type display, you can do these sort of math functions in it. So display 50 miles per gallon times the coefficient for miles per gallon plus 2,142 pounds times the coefficient for weight. The answer is around 13,600 pounds, or the ratio that I actually used was 13,591 to 13,599. But that's the trick, is the constant is still a coefficient that you're estimating. So if it is statistically insignificant, you treat it as 0 as well. It's just normally we aren't dealing with the constant that much. So because we're not interpreting it, it's not generally useful to you. So we don't deal with it that much, but that's sort of the point of this question being in the practice, is to make that clear. All right, on to 9. Same regression output table. What is the probability that all of the coefficients on this regression are statistically 0? We come back here. This can be found by this f-test up here in the top right. This is the total f-test, or the test of total significance. And this is, what is the probability that the miles per gallon coefficient is 0, the horsepower coefficient is 0, the acceleration coefficient is 0, and the weight coefficient is 0, all at the same time. And that probability is 0.0001. And that's what I said, copy the entire number from the regression output table. That's what I meant, like, you don't need to put this into a percentage form. If I tell you to copy the number from the table, just copy the number from the table. Don't try to put a percent into this or anything, just copy down this number. And if I try to get you to give me a number from this table, unless it's an r squared and I ask in percentage form, it will generally be just copy the number, and that's what I'm wanting you to do. All right, on to number 10. We have two regressions, regression A and regression B. So regression A has a higher r squared. Regression B has a higher adjusted r squared. So what that means is, if you aren't penalizing for lost degrees of freedom, regression A is better. But if you do have that penalty, regression B is better. So what that means is, regression A must have more variables, but some of them are not relevant. So regression A has more variables, so its r squared is higher, but regression B, by dropping insignificant variables, has a higher adjusted r squared. So the correct answer here is regression A has more variables, but some of them are not relevant. For number 11, consider a case where sample standard deviation of x is 4,232, sample standard deviation of y is 15,623, and the correlation between x and y is 0.68. What would the value of B1 be in this simple linear regression? So this is just an equation from before. B1 equals the sample standard deviation of y divided by the sample standard deviation of x times the correlation. So you just plug in your numbers, and your answer should be 2.51, with maybe just a little bit of rounding wiggle room here in the actual answer on the exam. But this is just, here's the equation, plug in your numbers, solve out your number. This is the equation for B1. Once you've gone through that big derivation that I did, this is what it ends up being. Alright, so here's a t-test. You know it's a t-test because you have a sample standard deviation. So default to the t-test if you don't have any other pressing reason to do otherwise. That is to say, if I tell you to do a z-test, go ahead and do a z-test. But if I don't mention it, it's a t-test. So historically, we have a height of 64. We take a sample of 61, find the average height of that sample to be 67, with a sample standard deviation of 13 inches. Would you reject or fail to reject the null hypothesis? And if so, what would the appropriate significance level be? So we have insignificant, 10% level, 5% level, 1% level. So we're going to calculate our t-score. We have our t-score equation here. X bar is our sample average, which was 67. Mu naught was 64, which is our presumed height, the historical value that it has been. Our sample standard deviation is 13, and the sample size is 61, so the square root of the sample size. And this will come out to about 1.802. Then we need to look up, we have 61 students. We're doing a t-test, so we're going to lose a degree of freedom. So our degrees of freedom will be 60. And if we go to our t-table, what we're going to want to look for is a two-tailed test, because it was different from the historical average, not greater than or less than. Because we're looking for it to be different from, we're looking at a two-tailed test. We have a 60 degrees of freedom, so we're on this row. And we're going to come over, 90% confidence is 10% significance. Those two things are equivalent statements. So 90% confidence, 60, 1.671, and then 95% two-tailed was 2, 99% was 2.66. So we have our critical values that we're going to compare our answer to, 1.61, 1.671, and 2. So we come back, our answer is 1.802. 1.802 is larger than 1.671, which was at the 90% confidence level or 10% significance level. So 1.802, larger than 1.671, so we reject the null at the 10% significance level. At 95% confidence, or 5% significance, our critical value is 2. 2 is greater than 1.802, so at the 5% significance level, or 95% confidence level, we fail to reject. So this is not statistically significantly different from 0 at the 5% level. So the answer is, it is significant, so it isn't A. It's significant at the 10% level, but it's not significant at the 5% level, so the answer must be B. It's significant at the 10% significance level. So for 13, we have a minimization problem. We're going to see what is the appropriate first order condition for minimizing this kind of a problem. So we have set up minimize here. First step when you're doing these kind of a problem, or at least what I recommend you do, is multiply out the squared term. Again, when you get more comfortable with these kind of problems, you can just use the derivation rules directly. But for right now, for simple problems like this, I think expanding it out will be helpful for you. Then the first order condition, because we have a minimization problem, first order condition, take the derivative of this and set it equal to 0. derivative with respect to b. So xi squared is not affected by b, so it becomes 0 when you take this derivative. This part, negative 2xib, well, b, derivative of b with respect to b is 1. So this will end up being negative 2xi. And then the derivative of b squared with respect to b is 2b. So the answer will be the sum I equals 1 to n, negative 2xi plus 2b. For me, this is a here, but again, your answers are going to be randomized. So I don't know which one it'll actually be for you in terms of A, B, C, or D, but this is the correct answer, and here's the work of how to get it. 14 is just a little bit of a are you paying attention kind of a question, and how well do you understand what these symbols mean. C is a constant, and this sum goes from 1 to 27. It doesn't go to n like the other summation signs that we've dealt with are. This has a specific endpoint. So what this is C added together 27 times. So the answer for this is 27c. This is equivalent to saying multiply c times 27. Whenever you have a summation sign and a constant, you're effectively multiplying the constant by whatever your index number is up here. So in some cases, that'll be n, like when we do n times x bar in the previous video that I posted. But in this case, because n is a specific number, this is 27 times c. So now we have number 15. We solve through this. The expected value of x minus x bar times y minus y bar given x. The general case of this will end up being x minus x bar times e, the expected value of y given x minus y bar. And that's because this is just a test of understanding what a general case means. In the proofs that we were writing, we assumed that x and y were independent. But generally, we can't make that assumption. So if you didn't have the assumption that x and y were independent of one another, you could get to this part, but then you would have to stop, because the expected value of y given x rather, you don't know what this is, because these two things may not be independent. They may be dependent on one another. And without further information, all you can say is it's the expected value of y given x. So this is where you'd have to stop in a general case where you don't know that x and y are independent, because you can't make the substitution in here that we did in the homework. 16 is just a synonyms question. What is the expected value of y given x if y and x are independent? It's the expected value of y, which is the mean of y, which is y bar. It's all of these things. The expected value of y is the mean of y, is also y bar, is also the expected value of y given x, assuming that y and x are independent. So the expected value, there are many different ways you could interpret these things. For example, if I wanted to be more confusing, in this question, I could have replaced y bar with the expected value of y. However, I didn't feel like that was very useful to do. So I generally I prefer using y bar instead of expected value of y. But these two are equal, they're equivalent. I could use either one. So every time you see y bar, you're seeing the expected value of y, which is also the mean of y. It's just something to keep in mind that things that look confusing because you haven't seen them before, you may have. It's just a different way of expressing the same thing. All right, here we have 17. We have a sequence multiplied by itself. So x1 added up to xn times x1 added up to xn. And the best way to get to this is you would have a double summation xi times xj, which would cover x1 times the entire second summation, x2 times the entire second summation. And that's, again, I'm just trying to stress the point that the double summation that we have right here is just, it's exactly that. It's x1 times everything in the second parentheses. So I equals 1, and then you go through all of the j's. Then you go to I equals 2, and then all of the j's, etc. So the correct way to express this out of these options would be here. Double summation I equals 1 to n, and j equals 1 to n, xi times xj. Final one. Again, this is from our proof writing. We have the same sequence multiplied by itself. And we can write this as the sum I equals 1 to n of xi squared plus the sum I equals 1 to n j equals 1 to n xi xj. Now, in order for this to be valid, we have to specify that I does not equal j. Because all the cases where I and j are equal to one another, they're in the first part of this summation. If I and j equals one another, that's the same thing as saying xi squared, because it would be like x1 times x1. Well, that's just x1 squared. And if you pull all those out to the front, then those numbers aren't here anymore. So in this double summation, you have to specify, if you pull out the squared terms into the front in their own summation, like I did here, you have to specify that they're not in the second double summation right here, and you do that by saying that I does not equal j. So I hope this will clarify. The test will be very similar to these. You'll have some questions like this one, where you're taking a step from a proof that we did in our previous homeworks. So just going from one part to the next step. You won't have to do the full thing in sequence because that would be kind of difficult and it wouldn't be necessarily fair, because it could end up you make a mistake on one part and that would knock out the entire proof. But there will be steps that you'll have to do that'll reference the proofs that we've written. That'll be sort of like 18, 17, 15, all these sorts of questions. There'll be some algebra and calculus where you're trying to do the minimization problems. Sometimes you'll have to solve them all out like numerically, like we had in an earlier question. Or it might just be, here is the first order condition you would need. You take the derivative and set it equal to 0. You'll have some calculating a t-score, like in our previous exam. You'll have some equations that we've talked about, just plugging in numerically. There will be conceptual questions about how do you interpret different regression output tables. There will be a big focus on interpreting regression output tables because I think that's a very important skill for you to learn and just become very comfortable with. That's a lot of what you end up doing in econometrics, is interpreting what these regressions are telling you and understanding what does an unusual answer look like, what does an answer mean in context, and so on. Making predictions like this and here. So if you started plugging in these numbers, what would you predict the price to be? That sort of thing. This is from the previous exam, confidence interval of proportions. Again here, optimizing an equation numerically. But then a lot of interpreting data output and understanding how to interpret the tests and what do the coefficients mean. Interpreting the coefficients a little bit. That's what I want this exam to be focused on. And just to be clear, the cumulative part, or just what I've shown here, where you're going to be doing some t-testing, maybe some z-testing, talking about the test of proportions maybe, calculating some standard errors, that numeric part of the previous exam is mostly what I'm talking about for the cumulative. But also interpreting regression output tables, plugging in for different equations. Then you have doing the tests on regression output tables, interpreting if something is significant or insignificant, f-tests and how to interpret the results of the f-test. How would you interpret the difference in, like here it was a price difference between two cars if one is 10 miles per gallon better, assuming everything else is equal, and so on. And then you'll have some parts of it where, referring back to your proof writing, can you figure out how to go from step 1 to step 2 of a proof? And that would be the question. You'll have a selection of options of different combinations of summation signs and expanded form and so on. And the idea would be, do you know how to recognize what the correct next step of the proof would be? But I'm not going to, for the proof writing component, I'm not going to have it set up to where if you make a mistake in one question, that will negatively affect an entire sequence of questions. So it's not that we're going to have here's step 1 of the proof, here's step 2 of the proof, and if you get step 1 wrong, you'll get step 2 wrong. That's not how this test is going to be set up. You'll need to know how to go from step 1 to step 2, but then the next question about it might be disconnected from that. It won't be the same proof, or it might be from a different step later on. So if you mess up one, it doesn't mean that you'll mess up all the others, is my intent for that. So I hope this was helpful and clarifying, and if you have any questions, let me know.